Hi guys, BuildZoid here, and today we're going to be doing, and I'm on the wrong layer, aren't I? Please don't. Yeah, I am. Today we're going to be doing a PCB breakdown of a RX 5700 Red Dragon from Powercolor. The pictures of the card are from Tech Power Up, so huge thanks to them for providing high-res PCB pictures like this, and there's going to be a link to their review of the card down in the description below. I strongly recommend you check that out. I think they write awesome reviews, and plus they provide me with awesome pictures for for these videos. So with that out of the way, let's get into what Powercolor has done here with the card. So as far as I know, this is actually the same PCB that you would see on the 5700 XT Red Devil, and I mean Red Dragon. It's really like I'm sorry, Powercolor. As like I'm a fan of dragons. Okay, so it's no problem with it being called the Red Dragon. The problem is if both of the freaking if both cards in your lineup start with the same letter, I'm gonna screw them up. It's kind of like I'm just gonna make mistakes like that. So. Though technically, actually, the Red Devil also uses this PCB. The difference is that the Red Dragons remove these two phases up here. Which basically turns this PCB in terms of power delivery into what you would get with a RX 5700 XT Nitro Plus from Sapphire. So yeah, I'm kind of a big fan of what Powercolor is doing with their 5700 series lineup because, these are like these cards don't break the bank like say the Strix does, right? Like that one's horribly expensive, and basically all of these have better PCBs than reference, which can't be set well. Yeah, for so the 5700 XT version of this technically not better than reference. It's a side grade, but this against the 5700 reference card is a straight upgrade, and the Red Devil is also a straight upgrade from the reference 5700 XT. So anyway, I'm kind of a fan of what they're doing here. And yes, this is actually like power stage wise, controller wise, this is the same card as the Sapphire Nitro Plus, which is also why, which makes things easy for me because I already wrote the script for the Nitro Plus. So I've just notes. I don't write scripts. So I've just copy pasted that right over. And yeah, we can, though there are some actual like differences in terms of like how Powercolor has chopped off phases, which I'm a big fan of, like compared to what Sapphire did. So, with all of that useless, pointless talk out of the way, let's take a look at what Powercolor has actually done here. Starting with, of course, the VCore VRM, which is this right here. So that's our VCore. And actually, I don't want to write over that area because we're going to talk about this right here. So that's our VCore VRM. It's a 1, 2, 3, 4, 5, 6, 7, 8 phase. It is controlled by the IR35217 over here. So that's running in 4+2 phase mode. So, because you're not getting 8 phases out of this controller. Otherwise, it only goes up to 8 total. So, I mean, 4+1 there. So the 4 then goes into times 2, which is done via IR3599s, which is that chip, and also this chip. So those are the 3599s. Those are doublers. International rectifiers, doublers, they don't current balance themselves. But the controllers that IR makes are actually smart enough to distinguish between the two phases even after a doubler. And so they can current balance through a doubler, which is kind of neat because a lot of other manufacturers, they have to have their doublers do the current balance. Well, it's kind of, I'm not sure that it really matters that much because like what part in the control chain does the current balancing is just kind of like, I think it's mostly a preference thing for the manufacturers where it's like, well, if we put that functionality, like if you put that functionality into the doubler, it makes the controller cheaper because the controller can be a bit dumber for it, right? Where the doubler will just spit out an average current to the controller and the doubler will worry about maintaining current balance and the controller will just kind of not, will worry about maintaining current balance over the actual, like, over the 4 phases that it sees. But though I guess the thing is if you do it through the controller, with dumbed, like if you do it IR's way, then actually the controller can balance every single one of the 8 phases instead of just the doubler balancing the two phases after itself. So yeah, different approaches to solving the same problem. And I guess the IR method, it ultimately works out best. So anyway, but there's no doubling in these, so if you used a different controller, yeah, you don't have current balance. The other feature these have is they can quadruple, but there's very, very few motherboards that actually, motherboards or GPUs. Actually, I don't think there's a single GPU that has ever taken advantage of the quadrupling capabilities of a 3599. Motherboards there have been, but I've never seen a quadrupled a GPU. Yeah. There is a GPU which I thought was quadrupled, but that actually turned out to have dual doublers in one pack, like just a chip that you put two PWM signals in, four come out. But anyway, nobody cares about that stuff, do they? So yeah, but that's the control scheme here. And the one downside to using the doublers is they do add a very, very small, like 5 to 30 nanoseconds delay onto your PWM signal. So you get slightly, very slightly worse transient response because a lot of modern controllers have a lot of sort of clever PWM tricks that they can use to get better transient response. If the PWM signal arrives a couple nanoseconds later, the tricks are, slightly less effective than they would normally be. So that's kind of the downside, but I'd like there's ways to work around. Like you can also just use more capacitors on the output. That's another option. So. And speaking of capacitors, this is actually the thing that I really, really like about this card. Yeah, we're not going to look at the power stages yet. So the other card that sort of uses a 10-phase V-core layout and then lops off two phases, the Sapphire Nitro Plus, well, that card, it also lops off all of the output filtering for those two phases. Powercolor here doesn't, which I'm surprised that the only thing they took off is the power stages and the they basically took off just the power stages and the inductors as well as the passives necessary for supporting the actual power stages. Like the output side of the VRM is completely unchanged, which basically there's more you have two extra, if they didn't do this, then you'd have two less aluminum polymer capacity, through-hole aluminum polymers. And also on the back of the card, which this is, I think, unique to Powercolor. Again, we see every single one of these multi-layer ceramics populated, which, I've not seen a single card do that. The thing is, most cards don't, don't have a 10-phase available, right? So they don't even have, these top three rows of capacitors. That's just not present on a lot of cards. So you don't even, you can't populate that. It's not there. But then in the rows that they do have, they'll just leave out that cap or this cap, or they'll just leave out one cap in each row or two caps in a couple rows and one cap in the rest of them. So you never really see an RX 5700 or 5700 XT with a fully populated output capacitor configuration for the output of the V-Core VRM. So yeah, I'm a big fan of that. I don't think it makes a significant difference to the actual overclocking capabilities of the card. It might be 10 megahertz, maybe. And of course, 10 megahertz, the issue is you're going to see more variance from Silicon Lottery than from, basically if you buy 10 cards, you can kind of ignore, if it's going to be a 10, 15 megahertz difference, which honestly, I'd be surprised if this is a very slight adjustment, right? I'd be very surprised if it made even that much of a difference. But hey, I'm still a fan of the fact that they do have a couple extra capacitors. It's just I don't think practically it would achieve anything. And I think that's the main reason why most of the other add-in board partners, they don't bother with these, right? They just remove as many capacitors as they can within, the restrictions of does it still meet spec. But Powercolor seems to be just there's pads here, so there will be components there. So yeah, I'm a fan of that approach because we all know how I feel about unnecessary capacitors, right? Especially on the output of a V-Core VRM for a GPU. Now, this the input filtering capacitors missing, that's just normal because you don't have the phases there, so that's fine. That doesn't matter. The whole point of having this capacitor and then probably that one, I'm not sure, And then if we go on back of the card, and then like this one right here, like that one's missing there. So these are to basically deal with the switching noise from the power stage, and there's no power stages there, so there's no point having that. Like, well, you might see some benefit, but it would be really like, like pointless as far as I'm concerned. Interestingly enough, 16-volt capacitors tend to be more expensive than 2.5-volt capacitors, so it's just like, I guess that's why these got prioritized for removal. Or this is an engineering sample board, but I doubt that, because we're so far, like we're so past launch for most of these custom cards that I don't see why they'd be shipping engineering sample boards to people for testing. So anyway, yeah, I'm a big fan of the fact that, like, Powercolor, they literally only removed the phases as far as I'm concerned. Like, that's the only thing that's missing. And the end result is that basically the VRM gets, well, compared to a reference RX 5700, this is better than the reference PCB. Compared to a 5700 XT, it's a side grade, because the 5700 XT reference PCB is a 7-phase using 70 amp smart power stages. This, as we've already gone over, is a 8-phase using doublers from a 4-phase to get to the 8 phases, with a bunch of NCP 302155s, which seem to be like the default for most RX 5700s. And these are 55 amp power stages from on semiconductor. They are not exactly, like, they're not on the same, level of efficiency as like a 70 amp smart power stage. It's just a complete, like, massive difference in there. And also these aren't like, these are just straight power stages. They basically, like, they don't even have a built-in like method for monitoring temperature. They just have an over temperature line, so they can tell the controller, hey, I'm overheating, but they can't actually tell the controller what temperature that is. Now, there is still, of course, going to be temperature monitoring in the VRM, because it's necessary for things like load line setting, current sensing accuracy, and there's just like, so, and I'm assuming it's that right there, or it might be because, yeah, I'm not really seeing any like suspicious, because there's going to be like one temperature sensor in the entire VRM, and I don't really see anything that you just have one of anywhere else. So it's like, that's probably the temperature sensing. Also, since they aren't smart power stages, you do get the external current sensing, which is what this right here is. So that's what's going on with that. If anybody was wondering, that's not part of the output filter for VCore. That's just current sense. So anyway, back to the front of the card. But yeah, so we have 8 phases of the 55 amp power stages, and the end result is that for efficiency, you're looking at the following figures. 1.2 volt, well, at the following operating parameters for the VRM, it should produce the following sort of efficiency figure. So 1.2 volt, well, efficiency, heat outputs. You can convert it into efficiency if you do some basic math, right? Like, that's why I don't bother with including efficiency numbers. So 1.2 volts, 500 kilohertz, and 5 volts drive, which is, like, that's just what these run on. And I think that's this regulator down here. That's probably our 5 volts, because, yeah, it's very small, and it's in a, like, it's in a location that doesn't make sense if it was feeding the core. So anyway, and there's like regulators for everything else already. So anyway, 500 kilo, so that's our operating parameters. And the efficiency is 150 amps output at about 15 watts of heat. So that's great. That's actually a really good efficiency number right there. 200 amps output at about 21 watts of heat. 250 amps output at about 28 watts of heat. And 320 amps. Unfortunately, the data sheet for these stops at 40 amps because, yeah, I know they're called a 55 amp power stage, but if you actually run them at 55 amps output, they're going to produce so much heat that, especially in like an 8-phase configuration like this, you're just not going to be like, maybe if you smashed a water block on it, that might actually be a current output you can sustain thermally, but not like any other way. Like, you need a lot of cooling to get the maximum current output out of basically any power stage. Like, that's just kind of like, just because the power stage is rated for 60 amps doesn't mean you actually want to push 60 amps through 8 of them at once. Okay, it does not work like that. Anyway, 320 amps output, the VRM would be producing about 45 watts of heat. So against a reference 5700, this is just a straight upgrade. Against a 5700 XT reference PCB, it's basically a side grade. The 5700 XT actually wins basically by like a watt or two from like 200 amps up, the 5700 XT reference PCB starts pulling away because 70 amp smart power stages are just insanely efficient. And there's 7 of them, whereas, here we have 8 of the 55 amp power stages. And, yeah, that just so works out that the 70s have a bit of a efficiency advantage overall because, yeah, we have one phase more, but the efficiency of each phase is slightly lower, especially at the really high current outputs. So, that's kind of that. The good news is that if you're running a 5700 at like stock settings, you're probably going to be running somewhere between 150 to 200 amps. If you're running a 5700 XT, you're going to be running slightly like more towards the 200 amp end of that, not towards the 150 amp end. So yeah, this VCore VRM also, this is also the same efficiency that you'd see. This should be the same efficiency that you see on a RX 5700 XT Nitro Plus PCB because that one has a very, very similar VRM. So yeah, that's like I'm for a 5700. I'm a big fan of this VRM. For a 5700 XT, it's like, well, it's a side grade. And the thing is, the Red Dragon is by far not like for Powercolor. The Red Dragon is more like, it's not their flagship card. So I think this is because they have like a low cost card, then they have the Red Dragon, which is like their mid range, and then they have the Red Devil. And I think this for like a mid range offering is great. Because a lot of the other cards, like, I mean, this again, same PCB, like, well, similar power delivery capabilities as a 5700 XT Nitro. So yeah, because a lot of the other cards, they just straight down, like they're just straight downgrades from the reference PCB from AMD. So, yeah, I'm a big fan of what Powercolor is doing with this. And in terms of cooling, like if you're on the air cooler, like the stock air cooling system of the GPU, it'll handle this no problem, right? Because you've got tons of airflow. The VRM's sunk directly into the fin stack of the GPU heatsink. So yeah, like this is no problem to like all the way up to 250 amps. Like it's not going to be an issue to deal with. 320 amps, you'd probably be looking at like very, very high fan speed, but also I don't think you're going to hit this unless you're on like liquid nitrogen or something. So yeah, that's the VCore VRM. We basically have the, like, if I did a VRM tier list, this is like for 5700s in general, then it would go like Strix, Red Devil, this. Well, no, not this. Reference card, this, Nitro, and then everything else. So top 4, I guess that makes it. Yeah, it makes it top 4. Except this is like on a 5700, so I'm a big like I'm a fan of that. So I think I've said that so many times now that it's just like, yes, this card gets the seal of approval. Now the other thing that I really like about this card is there's a BIOS switch. And, it has a PCB that is identical to the 5700 XT Red Dragon. It has a BIOS switch. It's a 5700. You can flash 5700s with 5700 XT BIOSes. This is made much easier when there's no difference in the PCB between the card you have and the card you're flashing up to. So yeah, like if I got this card, basically the first thing I would do is grab a 5700 XT Red Dragon BIOS and like stick that on here. And that would be like, and actually I'd probably leave it at that. I wouldn't even you wouldn't like, that would already give you such a, like that should get you like, so normally a 5700 is like, well, a 5700 XT is like 10% faster, 11% faster than a 5700. If you put the BIOS on, you're probably going to be, like the gap is going to shrink to maybe like 5%. So you could overclock it a bit past a bit more as well, and probably catch up to a 5700 XT quite easily. So yeah, and the BIOS switch means that if you do somehow manage to screw up the BIOS flash, like by flashing in the middle of a thunderstorm, or if you just have terrible power so it goes out while you're flashing your GPU, well, you have a BIOS switch, so you're not going to be completely screwed. Which you wouldn't actually be completely screwed. It's just far more convenient to recover from bad BIOS flashes with a BIOS switch, especially, well, if you don't have a secondary GPU like iGPU or like another card, not having a BIOS switch, you're actually screwed. But if you do have a BIOS switch, then it's just if you do have a second card, then it's mostly just a convenience thing. But hey, It's definitely a nice feature to have, since a lot of 5700, well, I'm actually not sure how many 5700s have BIOS switches. I've not really been paying that much attention to it, but still, it's like you have the BIOS switch and a PCB that is basically the same as the 5700 XT version, so I see very little reason to not just like flash these all the damn time. Like, I think that's like the most, because the other things that the BIOS flash does, it raises the clock ceiling, it raises the, now you could also do this with power, like custom power plate tables, but the thing is, if you just flash the BIOS, you don't have to mess with the registry at all. It's just like, now the drivers think it's a 5700 XT. Everything, you don't have to worry about it every time you update the drivers or anything. So yeah, I'm a big fan, like I would totally go and like flash the BIOS on this. Because you have the BIOS switch. So that's a cool feature. And then for the sort of rails nobody cared, well, I don't care about, we have VMEM in the usual split two-phase right here. So actually, wait, so that's our VMEM, which I'm like, at this point, I am like, well, I'm not 100% certain, but I really think this oddball layout is to like get more even power distribution across the power plane of the GDDR6. And there is one card that doesn't do this, and that's the Strix, and they just kind of jam all of the memory power over here. But everybody else, for some reason, has it like this. And like from a heatsink design perspective, like this is actually kind of awkward because like you basically have to squeeze your heat pipes through there. It's a nightmare for LN2 pots, but nobody really cares about that with 5700s. So yeah, anyway, so we have the two-phase VMEM up where it is. And for that, we're looking at yet more of the NCP 302155 power stages. If this was outputting, say, 40 amps, it would produce a little, which is way more current than the GDDR6 will ever need, because it runs on 1.35 volts. If it pulled 40 amps, like basically 50 watts of the GPU's total power draw would be going straight into the memory chips, which is not the case. For like GDDR6, like 8 gigs of GDDR6, is it 8? Yeah, it's 8 gigs of GDDR6. It's not going to pull that much power. It is 8, right? Yeah, it has to be 8. 16 is stupid for 5700. Anyway, so 40 amps, this would be, the VRM would be producing a little under 4 watts of heat. And, you know, it's spread across, well, it's as far apart as it possibly could be. Like, I'm really not concerned about those two phases overheating. The controller for that is the NCP 81022 over here. That thing is kind of neat because there's a full public data sheet. It's very easy to hard mod. So if you wanted to mess around with tweaking the memory voltage, which GDDR6 should scale with memory voltage, except of course, you know, does AMD's memory controller like allow you to push the GDDR6 further? I'm not sure. But yeah, it like, this is super easy to mod. So if you want to, you know, if you're brave and you want to see, you know, if you can push the memory a bit further, then just look that up. Because you can like just search this on DigiKey. They have a data sheet, or they should have a data sheet. Anyway, so, and that's running in a 2+1 phase configuration. So the 2 is of course the VMEM, and then the +1 is this down here. And that down there is what I assume is the VDDCI. And that is the memory controller rail. You can also mod that because it's running off of, well, it's running off of the NCP 81022. Just with this one, I'd be very, very careful because memory controllers tend to, like, compared to like GPU cores or memory chips or really anything else, memory controllers have a bad habit of dying if you raise the voltage, like even a little bit too much. Yeah, so just like I would not... Like, I would strongly not recommend messing with that one unless you have, like, backup GPUs, right? Because that one is a really easy way to just destroy your memory controller. Because you can, like, you can tweak it a couple, like, if you set it, say, 200 millivolts above stock, that could already easily be way too much voltage for the memory controller, which with most other things, like, it's not that bad. Also, memory controllers, when they don't really, like, well, they can degrade, but more often than not, they just straight up die, like lose memory channels or just start causing artifacts all the time, just, you know, go really, really bad, really, really fast. So I'd be very careful with that one. Anyway, that's another NCP 302155. And that will produce, if it was pushing 20 amps, which is probably way too much for VDDCI, though actually, like, the funny thing about the memory controller rail on AMD GPUs, it does actually pull a significant amount of current. I'm just not sure how much it is for the GDDR6 one. For the GDDR5 one, 3 gigs of GDDR5 would have the VDDCI pulling like 10 to 15 amps. So it's not like a super low current rail, but yeah, I'm not sure how the GDDR6 one compares. That one might actually be worse than the GDDR5 one just because it's a higher frequency. But anyway, even if this was pushing 20 amps, it would produce a little under 2 watts of heat. So yeah, I'm really, again, like, there's nothing else really producing. Well, there's memory chips next to it, but I wouldn't be too concerned about this overheating. And then down here, we have another single phase regulator using the NCP 302155. This one's probably this one's running off of the IR35217, so this one would be an absolute nightmare to volt mod. And that is like same heat output for the same amount of current, and I assume that is the SoC rail. These two, the VDDCI and the SoC, might be switched around. In which case, that might actually be to your benefit because you like SoC might not die as quickly as VDDCI does, right? So yeah, anyway, that's the VRM configuration on one of these. Is there anything else I'm forgetting? I don't think there is. No. Yeah, so basically, you know, like over stock RX, like basically as far as RX 5700X 5700s go, this is definitely one of the nicer VRMs you can get. As far as 5700 XTs go, this is not the worst one you can get. That's one way to put it, because there's actually not that many variants of the VRMs that you can get. Like there's the Strix, Red Devil, reference card, Red Dragon, then you get the like the 7-phase with 60 amp power stages, and then you get the 7-phase with 55 amp power stages. And those are the only variants I've seen. And somewhere in there's also the RX 5700 reference card, but I can't actually, like, I don't remember where that one places exactly right now. I think it probably matches the 7-phase 60 amp configuration. So anyway, because that's a 6-phase 70 amp smart power stages configuration. So yeah, that's the Red Dragon. Thanks to Tech Power Up for providing the pictures of this PCB of this card, because yeah, I mean, otherwise I wouldn't be able to do videos like this. And props to Powercolor for making a for basically just taking the Red Devil PCB and you know, like they lopped off 2 phases, which admittedly that's probably like maybe $2 to $5 worth of components depending on stuff. So it's not exact. Oh wait, I did forget something. I did want to mention all of the capacitors on this card all of the aluminum polymers on this card are APAC. So that's the Taiwanese cap maker, and they're aluminum polymers, and they're rated for 5,000 hours, which it literally says on them, 5K. So yeah, 5,000 hours at 105 degrees Celsius. But I don't think, like, if I remember correctly from the Tech Power Up review, this doesn't get that hot. But you can go check the review if you want to know for sure. So yeah, there's going to be there's a link to the review of this card from Tech Power Up down in the description below. Thanks to them for providing the PCB pictures. And then that's it for the video. So I guess like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon where you can support me directly. And if you'd like to buy some like AHOC themed merch, there's a Teespring store. There's shirts, there's stickers, there's posters, there's socks, there's hoodies. So I think I just listed off everything that's there. So yeah, if you'd like to check that out, that also helps out immensely with running the channel. So thanks for watching, and goodbye.